Okay, kids, so we're moving on to the next section, section 7.4, and it's called electric potential. Now, before we dive into this, let's take a step back here and do some reflecting and comparison. So, one of the ideas that we've covered in physics is the idea of force, a push or a pull that will cause an object to change its motion, acceleration, happens, things like that. One of the forces we've been dealing with is the force of universal gravitation, F big G. We're very familiar with this equation right here, and as always, forces are measured in newtons, and we've done work with this. And look at the very similar equation we have for electrostatic force. All right, it's a force, so it's in newtons. And instead of the universal gravitational constant, we have the electrostatic constant. Instead of the force being caused by masses, it's caused by charges, but it's still dependent on how far apart the objects are. We have r squared in the denominator, forces. Then we moved on to the idea of fields, trying to describe the effects of an object beyond its physical limits. So beyond the Earth's gravitational field exists, and it applies a force in newtons upon other masses that are around it. So newtons per kilogram. And we've used this equation many times. Similarly, there was the electric field caused by charges. And, for example, if you've got a charged particle, all around that charged particle would exist an electric field. If another charged particle is brought in the vicinity of the first charged particle, it will feel a force which is dependent on the amount of charge present, newtons per coulomb. Then we had a very interesting discussion about universal gravitational potential energy, E big G, and we discovered it was all negative. And we went through this equation here, we did some questions, what have you, and it's an energy, so it's measured in joules, J. What we now have to do is talk about the electric version of this. It's very similar. See how the equations are so similar? It's still measured in joules, but what would be the sign here? Remember when we did E big G, by definition it became negative? Well, what is the sign here? Well, here, with electric potential energy, you have to recognize that electric force can be an attractive force or a repulsive force, depending on the types of charges involved. With gravitational potential energy, you have to recognize that the force is always attraction. All right, so since the force is always attraction, it's one of the consequences here is that we always have negative universal gravitational potential energies. That's not the case here. Sometimes it'll be positive, sometimes it'll be negative, and it literally depends on the product of the charges. What are these two charges? Are you multiplying two positive charges together? Then you'll get a positive electric potential energy. Are you multiplying two negative charges together? You'll get a positive electric potential energy. Are you multiplying a positive charge times a negative charge? Well, then you'll get a negative electric potential energy. A little bit of difference, but still, look at the similarities. It's amazing. It's amazing that if you really think about this, there is a simple, beautiful underlying uh, simplicity to the universe. So, in order to emphasize what I just finished talking about, let's graph electric potential energy versus r, how far apart two charged particles are. And when one of them is a negative particle and a positive particle, we have attraction, and the electric potential energy looks like this. Very similar to the graph for gravitational potential energy because it's attraction in both cases. When we're talking about repulsion, when one of the charges are negative, or excuse me, when both charges are negative, or when both charges are positive, the product becomes positive, and the graph for electric potential energy looks like that. Repulsion, graph is above zero. Attraction, graph is below zero. So here, your electric potential energy is definitely negative, but here, let me write it out, your electric potential energy is definitely positive. So we could do an example. Let's say you have a charge here. We'll call it charge QA. Let's say it's positive and this many coulombs right here, 5.0 times 10 to the negative 5 coulombs. And 0.52 meters away, there's another charge, QB. Let's call it negative QB. It's a negative charge. There it is, negative 5.0 times 10 to the negative 5 coulombs. And we would like to know the electric potential energy that is established between these two. Well, it would definitely be an attraction, so you know you'd get a negative value. Why would I get a negative value? Well, K is positive, QA is positive, QB is negative, R is positive. It's a distance, so this negative sign in the QB is going to dictate the product being negative, and you would have a negative electric potential energy. I think you can all plug in the numbers and find how many joules it would be. I think you're all quite capable of plugging in those numbers and finding out how many joules that would be. I'll leave that to you. Okay, I'm going to leave that one to you. Now with electricity, we're going to go one step further. It's a step that is usually not done for gravitation. It can be done, but it usually isn't. And it's called voltage, which is also known as electric potential. Not electric potential energy. We just finished that one. This is voltage or electric potential. Boom, done. Don't add the word energy. So electric potential is literally defined as electric potential energy per charge. So its symbol is V for voltage is equal to electric potential energy divided by charge. So it would be equal to KQ1 Q overall, and then you divide the whole thing by Q, and you get KQ1 over R. So in general, voltage or electric potential, here's a new equation, is KQ over R. The unit is a joule per coulomb, which is also known as the volt, which we talked about a little bit in grade 11. And now, why would we want to introduce this new quantity? Well, let me try to explain it to you with this sentence. First of all, voltage is a scalar quantity that is used to describe the electric influence of an electric charge beyond its physical limits. Sound familiar? I hope it does. Remember electric field? Do you remember that one? KQ all over R squared, and there was a directional sense to this, and we used it to describe the electric influence of a charged object beyond its physical limits, and it was a vector way of doing this. A vector way of doing this. Now we want to describe the electrical influence of a charged particle uh, beyond its physical limits, but we want to do it in a scalar way. That's really why this is used. Okay, so we got this new quantity called voltage. Let's graph it. So along here, y-axis, we'll graph volts, voltage in volts. And along here, R, how far are you from a charged particle? And this is what the graph looks like. If you have a positively charged particle, the graph will look like this. If you have a negatively charged particle, the graph will look like this. Can we make a connection between this quantity called voltage and other quantities we have already studied? Yes, we can, and that's what we're going to do next. So let's make that connection. Let's say that at this point here, R, away from the center of a charged particle, We scroll up to here and we say that's the 1 volt spot for a positively charged object. Well, what does that 1 volt mean? Well, it means this, and it's based on a small positive test charge. The 1 volt mark right here is the voltage at a point around a charge if 1 joule of work is required to bring a 1 coulomb test charge from infinity to that point. This point right here, R meters away from the center of the charged particle. Let me repeat that. If you, let's pretend here, I'm going to change this. Let's pretend this represents a 1 coulomb test charge, my little waving eraser. Let's pretend that's a positive 1 coulomb test charge. And let's pretend that way out here is infinity. So if I start moving this positive test charge closer and closer and closer to the positive big Q test charge that I'm investigating here, when I get to this point R, away from the center of the positively charged particle, so I've gotten to here. I started at infinity. When I get to that spot and I have done 1 joule of work to bring these two positively charged particles together, I am at the 1 volt spot. And that is making a connection between energy and this thing called voltage. So let's do a few examples here. Let's say I've got my 1 coulomb of positive test charge, there it is, and I'm at infinity. And I'm bringing it closer to this other positively charged particle right here. Well, there's a repulsion going on here, so I'm working against it, doing work to bring this positive test charge closer and closer and closer. When I get to here, I've done, let's say, 0.25 joules of work to do that, to move it to this spot right here, which is a certain distance r away from the positively charged particle. I've done 0.25 joules worth of work to move this 1 coulomb positive test charge here. So this is the 0.25 voltage line or circle. And it would mean that I am on this circle. So if it's a circle, the radius is constant on a circle. So I'm at the same distance away from the center of this yellow positively charged particle I'm investigating. So what it basically means is if I take this 1 coulomb of positive test charge and I bring it to here, or to here, or to here, or to here, anywhere on this circle, I'm doing 0.25 joules worth of work. So all along this circle would be the 0.25 voltage line. Similarly, if I bring it even closer, let's say I bring it to somewhere on this circle, I would have done 1 joule worth of work to bring it even closer, all right, from infinity. So that's the 1 volt line. If I bring that 1 coulomb, a positive test charge, even closer to this yellow positive charge we're investigating, let's say I bring it somewhere on this green circle here, well, if I bring it that close, I would have done 3 joules worth of work. So I denote this as the 3 voltage line. Okay, we'll keep going with this. If you have to pause the video, rewind it, slow it down, you do that, okay? Now, let's deal with investigating a negative charge. All right, so let's say I start right here, somewhere on this green circle right here, and I have a positive 1 coulomb test charge. If I start somewhere on here and now remember it's a positive test charge, so I'm moving it away, I'm working against the attraction, I'm pulling it away, and then I finally get to infinity, wherever that may be. When I get to infinity, I would have done 4 joules worth of work. So this is my negative 4 volt line. right here. If I start from anywhere on this circle and I take a positive 1 Coulomb test charge and I bring it to infinity, I would have done 4 joules worth of work. So that's my negative 4 volt line. It's negative 4 volts because I'm bringing it to infinity. All right? If I were to release it, start from infinity and bring it to there, I'd actually be doing negative work because I'm moving along with the attraction. So this would be my negative 4 volt line. Let's say I start with a positive 1 Coulomb test charge here, somewhere on this bigger circle. All right, I start with my positive 1 Coulomb test charge right there. And let's say I'm working against the attraction, right? It's a negative charge I'm investigating with a positive 1 Coulomb test charge. And I'm dragging out, working against the attraction. And I bring it way out to infinity. And when I got to infinity, I would have done 0.25 joules worth of work. Well, that means I started on the negative 0.25 volt line right here, this larger circle. Okay, hopefully that helps. All right, well, we're back and I've added some links to today's announcement. Here's one that's showing a positive charge right here, and it's trying to show voltage, and see how it's very bright here in the close to the charge, and the lines are very close together. Now, it's just trying to show you uh, in a scalar way that the voltage is much higher closer to the charge and compared to when you move further away. And you can change it. You can put a double charge, like, okay, and the two voltages would superimpose on each other and overlap. They would add together to create different, what we call lines with the same voltage, or what we call, listen very carefully, please, equipotential lines. All right. So they interact with each other. Here's another one. A dipole, one's positive, one's negative, so positive voltage is shown in green all around this positively charged particle. Negative voltage is shown in red all along here around this negatively charged particle. It's just trying to help us visualize, okay? And look, in the middle it's dark because it's a sum of the two voltages, so it's literally zero in between here. Nothing there. Here's another one, another simulation that's out there, and it's trying to show voltage once again through brightness. There you have it. Very close to the negatively charged particle, higher voltage magnitudes, and the blue starts to fade out as you go away. Similarly, I could bring in a negatively charged, excuse me, a positively charged particle, and close to the positively charged particle, we have high voltages, they're trying to show with brightness, okay, and it fades out, just trying to help us visualize. Voltage has nothing to do with brightness, but ways to help our mind visualize these things. What we have here is a sensor, right? And I can move it anywhere I want. I strongly suggest you try this simulation, right? And you take a look here, and as you bring it closer and closer to the negatively charged particle, the voltage changes. Similarly, I can bring it closer and closer to the uh, positively charged particle. Look how the voltage changes. You try it on your own, kids. It's getting very, very high, close to the positively charged particle. And as we move far away, the voltage is less. So try these out on your own. Okay, well, let's try a voltage calculation. So let's say that right here is a positively charged particle. We'll call it Q2, positive 5.0 times 10 to the negative 5 coulombs. And then we go 0.26 meters away and another 0.26 meters away for a total of 0.52 meters, and we run into where another charge is. We'll call it charge Q1. And here, the charge on this particle is negative 5.0 times 10 to the negative 5 coulombs. And what we're going to do is investigate what is the voltage right here at this point in space. Well, the voltage at point A is going to equal the voltage at point A because of the presence of charge 1, so VA1, plus the voltage at point A because of the presence of charge 2. So the total voltage at this point in space we're calling A right here, that point right here, there's a voltage there, and it is due to adding the voltages that come about the two individual charged particles. Remember, this is all scalar now. So we plug in the values, k q1 over r1 plus k q2 over r2. Let's do some factoring here. So we factor a k out of each one. Now we're going to do plugging in numbers. So here's our electrostatic constant. The first charge is negative and it's 0.6 meters away. The second charge is positive and it's 0.3 meters away. No squaring in the bottom. You just plug it in the calculator and you get 7.5 times 10 to the 5 volts. All right, now let's take a look at that 0.6 and 0.3 meters. 0.3 meters was here, and through Pythagoras, I got the 0.6 meters right there. Pretty straightforward. How about the voltage at point B right there? The voltage at point B. Well, similar type of process goes on. The voltage at point B is equal to the voltage at point B because of the presence of charge 1 plus the voltage at point B because of the presence of charge 2. And then we do similar type of mathematical calculations. We plug in values, and lo and behold, the voltage there is zero. Zero voltage there. And that's the situation I have set up in this simulation. You might want to replicate this. Here's a negatively charged particle. Here's a positively charged particle, and I've got the sensor set up right there. Look, 0 volts right there. And you can move this sensor anywhere you want. Look, 0 volts there. That's probably the halfway point. Over here, the voltage is positive right above the positively charged particle, right below the positively charged particle. The voltage is positive, see? All right, right below the negatively charged particle, the voltage is negative. Right above the negatively charged particle, the voltage is negative. You can move this around and sense what's happening here. You can also, which is kind of cool, is hit the pencil button. Boom. And it starts to draw these equipotential lines we talked about. You see that? Oop, try to fix that for you kids. All right, it's kind of overlapping there, but you get the point. As I move this over, move it over here, and we can draw these equipotential lines. See how they're not circular now? They sort of bend away from each other when you are near where the 0 mark is. They're not symmetrical because I didn't pick exactly the right spots. All right, but there it is. A combination of the two voltages to give you an overall or resultant or net or sum voltage. And right along here, I've got the 0 line. Kind of neat. So let's try an example together, section 7.4, and let's do practice question 1. I'll read it to you. The electric potential, so the electric potential V, voltage, at a distance of 25 centimeters or 0.25 centimeters from a point charge is negative 6.4 times 10 to the negative 4 volts. And it says determine the sign and the magnitude of the point charge. So here's the point charge. We don't know the sign on it. We don't know the magnitude. We do know that at a point that's 0.25 meters away, right there, there's an equipotential line. It'll be circular. That is having a voltage of negative 6.4 times 10 to the negative 4 volts. Well, here's my equation for voltage, but now I want to solve for Q. So I rearrange it. I rearrange that equation for Q. Take a look there. And I get Q is equal to VR over K. I plug in the numbers, and lo and behold, here's my charge. All right, there's my charge. And it makes sense that it's negative because I have a negative voltage there. That makes a lot of sense. All right, let's try another one. Same page, section 7.4, practice question 2. Let's read it. It says it takes 4.2 times 10 to the negative 3 joules of work to move a positive 1.2 times 10 to the negative 6 coulombs of charge from a point X to a point Y in an electric field. Calculate the potential difference between X and Y. So there's an electric field set up here. Don't know how it's set up. I do know that it takes work to move this positively charged particle from point X to point Y. It takes a certain amount to move positive. Let me emphasize the positiveness of this. Positive 1.2 times 10 to the negative 6 coulombs of charge. It takes 4.2 times 10 to the negative 3 joules of work to move it from here to here. So since this value here is positive, I'm actually working against a repulsion as I'm moving this positive charge towards here. I'm working against a repulsion. So what is work equal to? Well, work is always equal to a change in energy. In this case, it's a change in electric potential energy. And the equation for electric potential energy is K Q1 Q2 all over RF minus K Q1 Q2 all over R initial. That's by the equations we know. But we know what KQ1RF is equal to. That's the equation for voltage. KQ1 over RF. KQ over R is voltage. So let's call that voltage final times Q2. Similarly, KQ1 over R initial, that's a voltage equation. So let's call that V initial times Q2. So now we're going to factor out a Q2 and we're left with VF minus VI, voltage final minus voltage initial. Well, voltage final minus voltage initial is just another way of saying delta voltage. All right, delta voltage. Or the difference in voltage, delta voltage, the difference in voltage. So I'm going to rearrange this equation. Work is equal to charge, work divided by charge is equal to the voltage difference, the potential difference. I know how much work it took. The question told me. I know how much charge I'm moving. So I divide the two and I get 3.5 times 10 to the 3 joules per coulomb. And a joule per coulomb is 3.5 times 10 to the 3 volts. Joules per coulomb is voltage. All right, so that's how we would do that one right there. A little bit extra long lesson today, I get it. I'm sorry about that, but this is a big topic. Make sure you read section 7.4. Make sure you do the questions I assigned you. Keep on working hard, kids. Just keep on going. We're doing the best we can. I have great confidence in you. I know you can do it. And if you have any questions, please let me know. And we'll talk to you later. Stay safe. Bye-bye.